In this module, we are going to continue from where we had left. In the last module, we had seen the solution of the Navier-Stokes equation, where we had obtained the velocity distribution for a flow through a circular pipe, which was given by this formula, and we went on to derive the expression for the bulk mean velocity, which came out as this, and we also had the maximum velocity, which was derived as this quantity. We established a relationship between bulk mean velocity and the maximum velocity. Now, we go to the energy equation, which I have already written for your benefit here. Remember, energy equation is a scalar equation. It has a coupling between the velocities and the temperature, and it is written in this form as shown here. So, we have to simplify this equation for obtaining the temperature distribution. So, differential equation needs to be solved. So, this is steady state, first assumption, u r is equal to 0, number 3, u theta or any gradient with respect to theta is 0. So, assumption number 7, we are left with this, no volumetric heat generation. So, no volumetric heat generation. This is, you can call this assumption 8. Assumption 9 is viscous dissipation negligible. The viscous dissipation is important only in high speed flows. You would have seen this during the derivation of the energy equation and the non-dimensionalization. So, viscous dissipation is neglected. This is assumption 9. So, this is slide number 13. Okay, assumption 8 was no volumetric heat generation. Assumption 9 is viscous dissipation neglected. Again, this is going to 0 because d by d theta of any quantity is 0. Now, to understand the relative importance of the temperature gradient, or how do we say this, gradient of the temperature. So, d by dr of dt by dr. dt by dr is the gradient of the temperature in the radial direction. This is the gradient of the gradient. So, dt by dr at r minus dt by dr at r plus delta r divided by delta r minus or whatever. So, you are talking of the second derivative. Similarly, dt by dz at z plus delta z minus dt by dz at a particular z over delta z is your d square t by dz square. This is your d by dr. So, this is r dt by dr. There is an r which is missing here, sorry. So, this is the second derivative. So, what I am trying to say is your gradients in the r direction are much significant because bulk activity of heat transfer is in this direction. So, in comparison with the second derivative in the z direction, if you do the order of magnitude analysis, this I am simplifying it this way, though there is a d by dr r dt by dr. The point I am trying to make is this delta t over z, which is of the order L, length of the pipe, L squared, whereas this is some reference delta t of the order capital R, and R is much smaller than L, therefore, R square is much smaller than L square. So, my gradient in the z direction, in the flow direction is neglected in comparison with the gradient in the r direction, second derivative in the r direction. So, that is why we are going to drop off this d square t by dz term, the dz square term, and I am left with u rho cpu dt by dz is equal to k over r d by dr of r dt by dr. This is what I am left. Okay. We also have u of r is equal to minus r squared by 4 mu dp by dz 1 minus r by capital R whole squared. We had u bulk mean, which was derived as minus r squared by 8 mu dp by dz, correct. So, we had also shown, I hope you remember, we had also shown from basic energy balance for constant wall heat flux condition. Remember, we are talking about constant wall heat flux condition, QW equal to constant. This is slide number 14. We had shown from basic energy balance that dt by, we wrote it as, for a control volume like this, we wrote it as m dot Cp dTm is equal to q double prime pi d dz, and therefore dTm by dz came out to be equal to q double prime pi d by m dot Cp. For a circular pipe, this is q double prime 2 pi r. M dot was nothing but rho u bulk mean into pi r squared Cp, and this was nothing but 2 q double prime by rho Cp r into um. And we said that this whole quantity, because heat flux is a constant, diameter is constant, rho Cp, everything is constant, this whole thing is a constant. Remember, we had come up with this, and we had also shown dt by dz is equal to dt wall by dx is equal to dt m by dz, this one is equal to this quantity. This was also shown couple of modules ago, so you can take a look at that. We are going to employ this here. So, let me go to this energy equation. This is nothing but u dt by dz is equal to k over rho Cp is alpha. So, alpha by r d by dr of r dt by dr. Nothing can be changed here except that we substitute now. So, I substitute for dt by dz as this quantity. So, this is u of z, this is local velocity. So, this is nothing but u of r profile. This dt by dz I am going to use directly from here, that is 2 q double prime rho Cp u bulk mean into r is equal to alpha by r d by dr of r dt by dr. So, left hand side let us simplify. So, slide number 15, LHS I am going to write u of r into 2q. So, what is u of r? We had derived this as minus r squared by 4 mu dp by dz 1 minus r by r squared, this quantity into 2q double prime divided by rho Cp capital R, and u bulk mean we had derived as minus 1 by 8 mu dp by dz. So, based on this I would write 4 mu 8 mu. So, I am left with 2 here, dp by dz cancels off, okay, 1 r cancels off with 1 r. I am left with left hand side is nothing but, sorry, this is r squared. So, there is 1 r left here still. So, this is going to cancel. So, minus signs will appropriately cancel, and I am left with 2 goes up. So, 4 q double prime 1 minus r by capital R square as it is divided by rho Cp and 1 r which is left behind. This is your left hand side. What is my right hand side? Right hand side is k over rho Cp r d by dr of r dt by dr. Okay. So, and k over rho Cp r d by dr of r dt by dr. This is equal to this quantity. Okay. So, I am merely going to equate these two. So, I write left hand side equating LHS and RHS. I get 4 q double prime by rho Cp r 1 minus small r by capital R whole squared is equal to k over rho Cp small r d by dr of r dt by dr. What cancels out is the following: rho Cp cancels, and 4 q double prime r into 1 minus r square. So, I get d by dr of r dt by dr is equal to 4 q double prime by k capital R. K comes down, capital R remains as it is, and you have one r which is lying here. So, that goes here, 1 minus r by r whole square. Now, let us take a look at this. K is a constant. This whole bracket here is only a function of r, correct. So, everything here is a function of r, therefore, this derivatives here is now going to transform to regular derivatives. So, this becomes d by dr of r dt by dr. Instead of partial derivatives, they become regular derivative 1 minus r by capital R whole square. Now, it is a matter of just integrating. So, slide number 16. So, first integration, I am going to integrate this. So, first integration gives me r dt by dr is equal to 4 q double prime by k capital R integral of this quantity r minus r cube by capital R squared. R integral is r squared by 2 minus r cubed. What is r cubed integral? R to the power 4 divided by 4 capital R squared plus C1. Divide through by r, I get dt by dr is equal to 4 q double prime by k r. This becomes r by 2 minus r cube by 4 capital R squared plus C1 by r. Second integration, T of r is nothing but 4 q double prime by k capital R. Integral r is r squared by 2. So, 2 into 2 is 4. R cubed integral is r to the power 4 by 4. So, this is r to the power 4 by 16 capital R squared plus C1 log r plus C2. Okay. So, two unknowns. So, two boundary conditions, I am going to write them here. Boundary condition is at r equal to capital R, T is equal to T wall, and at r equal to 0, dt by dr equal to 0. Two boundary conditions, this is 1, this is 2. Therefore, I substitute boundary condition number 2 in my expression here, first one. I do not use this because it is not so nicely manipulative. So, r is equal to 0, dt by dr equal to 0, left hand side is 0, substitute r equal to 0, I get C1 is equal to 0. This was exactly what we got in the velocity profile, correct. So, now BC1 T wall. So, T of r capital R is equal to T wall. So, TW is equal to 4 q double prime by k capital R, R squared by 4 minus R squared by 16 plus C2 implies C2 is equal to TW minus R squared by 4 minus R squared by 16 is nothing but 3 by 16 r square, correct. So, this is 4 by 16 minus 1 by 16. So, 3 by 16, 4 and 16 will cancel. So, you get this as 3 by 4 k, 1 r will cancel with one of the r's here. So, q double prime capital R. So, q double prime capital R. So, C2 is this quantity. So, I substitute for C2 and C1, therefore, temperature distribution T of R is nothing but 4 q double prime by k capital R, R squared by 4 minus r to the power 4 by 16 capital R squared plus T wall minus 3 q double prime capital R by 4 k. So, which I like to make it in a form which is nice. So, T of R is equal to T W minus q double prime by q double prime into R by k, everywhere that is appearing. So, I take it out, open the bracket. This one is just 3 by 4 as it is, minus sign is absorbed here. This bracket q capital R by k. So, I have introduced capital R outside, there is R squared by capital R here. So, this comes out to be R to the power 4 by 4 R to the power 4, this is the second term. This term comes out to be minus R squared by capital R squared. You can check this maths and this is your temperature distribution, T as a function of R, temperature distribution. Okay. So, this is only half the battle won. Now, what we are supposed to do after we get this temperature distribution, we go to get the mixing cup temperature or the bulk mean temperature, and this part I am going to go a little fast. So, T bulk mean temperature we have derived the expression and it comes out to be 2 by r squared bulk mean velocity integral 0 to r, r u of r T of r comma z dr. Please remember, this is at a given location T of r comma z, you fix the z location. So, this is T of r comma z in effect. So, this I substitute, I just show the substitution, I will leave the maths for you to work out. So, T bulk mean therefore comes out to be, T bulk mean is equal to 2 over r squared bulk mean velocity. What is bulk mean velocity? Bulk mean velocity was coming, you have an expression for the bulk mean velocity in terms of the pressure gradient, etc. So, this is the bulk mean velocity 1 by 8 mu dp by dz. Remember, we also had, let me just this one, u of r is equal to minus r squared by 4 mu dp by dz 1 minus r squared by r squared. This was my expression, and bulk mean velocity was 1 by 8 mu, of course, minus sign is there, dp by dz. So, if I substitute for dp by dz and 1 by 4 mu, this is nothing but 2 times bulk mean velocity, correct. This is 2 times bulk mean velocity, therefore, minus 1 by 4 mu dp by dz. What is coming there in the bracket here? This one. This is nothing but 2 times bulk mean velocity. So, I can substitute for u of r. Okay. So, u of r divided by u of m. If I do this, u of r divided by the bulk mean velocity, I get this as 2 r squared 1 minus r squared by r squared. Okay. So, these manipulations are going to be used directly here. So, if I substitute for all this and I write this as r squared u bulk mean integral is nothing but 0 to r u max. This can be written as u of r also can be written as u max times 1 minus r squared by r squared. What is u max? When r is equal to 0, you get u is equal to u max, which is nothing but this quantity. So, u of r was capital R squared, this one. So, this is u max into 1 minus r by r squared. So, I substitute this as u max into 1 minus r squared by r squared, substitute for t of r comma z. So, you put this expression here. You put this expression here. Please remember that this quantity has several r here. This has an r square, this has an r. So, when you bring this u max out, you have u max by u average. So, u average and u max are related by the factor 2. This also we had shown before in the last module. U max is 2 times u bulk mean. So, substitute all that. When I do the integration, I get T bulk mean is equal to 4 u divided by u bar T w by 4 minus q double prime r by k into 11 by 96. This is about 1 page of algebra which you will have to do it on the board or tell the students to do. It is a good exercise to do this integration separately, and once you get this, I am left with simplifying this. So, I get this cancels off, T bulk mean is equal to T w minus 4 cancels with 96, I get minus q double prime r by k into 11 by 24, which is nothing but T w minus, I multiply and divide by 2, 2r is nothing but diameter, and I get 11 by 48. And now, I am just going to do a little bit of manipulation. T wall minus T bulk mean is what I need. So, I take this q double prime d by k into 11 by 48 on this side. So, I get this part, and now I say what is my definition of Nusselt number? 48 by 11 is equal to q double prime by T wall minus T bulk mean into d by k into d by k. This is nothing but your heat transfer coefficient. Therefore, you get h bar d by k, which is nothing but the Nusselt number. Therefore, Nusselt number for constant wall heat flux case is 48 divided by 11 comes out to be 4.36. Laminar flow, constant wall heat flux, fully developed, and a bunch of other assumptions which we wrote there. Constant properties, incompressible Newtonian fluid, no variation in theta direction, no volumetric heat generation, viscous dissipation neglected. We also said that the second derivative of temperature in the flow direction is much smaller compared to d squared T by dr squared. Then we had the other assumptions from the hydrodynamics. With all these assumptions, Nusselt number for laminar flow through a circular pipe subjected to constant wall heat flux boundary condition. Fully developed flow through a circular pipe subjected to constant wall heat flux condition came out to be 4.36. Students would have lot of work in doing this integration. They should ensure that this whole process of integration is nicely completed, and therefore, from that we can get Nusselt number is 4.36. Now, we go to the set of slides here, transparencies which are here, and we say that, so 4.36 was the Nusselt number for constant wall heat flux condition. Now, the derivation for laminar flow constant surface heat flux, constant surface temperature condition is left as an exercise typically done in PG courses. So, Nusselt number would come out to be 3.66 in this case. Now, for other geometries, this would be seen in most engineering textbooks. So, I can have a circular geometry and you have these two conditions. For a rectangular geometry with varying aspect ratios, you have the table for Nusselt number for constant wall heat flux and constant wall temperature case. The one on the left hand side, first table is the constant wall temperature case. Notice that the Nusselt number for constant wall heat flux cases are always higher than that for the constant wall temperature case. There is also an expression for the friction factor which is given 64 by Re was the friction factor for flow through a circular pipe, and the coefficients are different. For a parallel channel you get 96 by Re, for a square channel you get 56.92 by Re. If you are talking of an ellipse whose ratio of the major to minor axis, which is nothing but if it is 1 it is a circle, you get 64 by Re again, same as this. If you are talking of an ellipse which is very thin, your ratio goes up to 78.16. Now, based on this we have this table for other geometries. If you are talking of the entrance length, Nusselt number is given by these formulae, and these are presented in most textbooks. So, you have noticed that you have Re PR into D by L. Certain correlations are based on the bulk mean and the surface temperature viscosity. These can be used appropriately. Average Nusselt number for thermal entrance length between two isothermal plates is given by this formula by Edwards. And if you are talking of turbulent flow, there is no special formula, you are just going to deal with coefficient correlation called as the Dittus-Boelter correlation, which is very common and very powerful. 0.023 Re to the power 0.8 PR to the power N. N is 0.4 for heating of the fluid, 0.3 for the cooling of the fluid, and the properties are evaluated at the bulk temperature of the fluid. Ti plus Te by 2 is what is used. There are other correlations which are there. One is the Colburn correlation. For smooth tubes you have 0.125 FRE into PR to the power 1/3, and friction factor is given this. So, we just complete this by showing another set of slides, which is the Petukov equation for the Nusselt number and Nilinsky equation here. These are also used quite elaborately in research work. Nilinsky correlation and Petukov both have the friction factor embedded in the Nusselt number expression. This is given as F by 8 into some Re function, PR function. The range of use of these correlations are also presented here. If you are talking of liquid metals whose Prandtl number is very small, PR between and less than 0.01, you have two correlations here for constant wall heat flux and constant wall temperature case. Nusselt number is obviously greater for constant wall heat flux case, and PR subscript S is there, where S denotes the Prandtl number needs to be evaluated at the surface or the wall temperature. So, the point here is various correlations have been developed, some of them analytically, some of them through fits to experimental data. Whatever be it, you need to understand that these correlations can be used within the range of data. For example, here Nilinsky should be used between this range. The Dittus-Boelter typically Re greater than 10,000. So, fully developed flow. So, keeping in mind your problem, you can go ahead with use of particular correlation and check whether the results are matching with experiment. If so, then you are doing fine. There are other special geometry like flow through annulus, which we are not going to cover typically in undergrad courses, which also involve exactly the same procedure that was done for flow through a circular pipe. Instead of the full area, you have an annulus area, so you have to account for it. And in non-circular geometries, you will end up using what is called as hydraulic diameter, which is 4 times the cross-sectional area divided by the wetted perimeter. All of us have seen this in fluid mechanics also. So, 4A by wetted perimeter would be used as a hydraulic diameter, and this could be used for square, circular channels everywhere, and also for the calculation of Nusselt number. You have H characteristic dimension is the hydraulic diameter here. So, with this we come to the end of the module for heat transfer in internal flow. We had covered very basic stuff, constant wall heat flux condition, constant wall temperature condition. We went in detail with constant wall heat flux condition, developed the velocity, temperature profiles, came and calculated the Nusselt number. Very powerful, useful tools for use in practical applications. Thank you.